In this video, we'll continue our look at trigonometric substitutions with a few more examples so you can see how each of our three equations can be used. So our first example that we did previously involved the x equals a secant theta substitution. Let's look at another one. So let's just get into some examples. Right, let's start with, let's do a definite integral now. So let's say we have the integral from 0 to 1, and we have the square root of 1 plus x squared dx, right? So when you kind of look at this almost looks like one of our arc length integrals, because it has the square root of 1 plus something squared. And it goes from 0 to 1. So this could be interpreted as an arc length integral. But this particular one, again, under the square root, we don't have a perfect square. And there is no basic u substitution that will work, right? Because we don't have anything as an x, for instance, multiplying our dx, right? So in this case, because our integrand is of the form a squared plus x squared, this radical indicates that we should use x equals a tangent theta, right? So this one will involve this form. So let's go. So a squared, that would be our 1. Right? And again, the assumption is that our a is positive. So that means a would be equal to 1. And then we're going to use this equation, x equals 1 times tangent theta, or simply x equals tangent theta. And this equation is going to allow us to convert everything over from x to theta. So in this process of conversion, we're going to change our differential, we're going to change our integrand, and we're going to change our limits of integration, right? So let's start with the differential. So our dx, the derivative of tangent, is secant squared, and then d theta. This is our differential form, so that's good. The 1 plus x squared, that will get converted over, and I'll do that again kind of off to the side. Let's look at the limits, however. So these are our limits for x. What we would like to find out are the corresponding limits for theta. So let's see. When x is equal to 0, using this equation, we actually end up with a trig equation to solve. So when x is equal to 0, we have that tangent theta is equal to 0. And remember our assumption that theta is between 0 and pi over 2? Well, in that first quadrant, or, actually not in the quadrant, but along the horizontal axis, if I take the arctangent of both sides, then theta would be the arctangent of 0, and that turns out to be 0, right? So the lower limit for x just happens to coincide with has the same value as the lower limit for theta. Well, let's see what happens with our upper limit. So when x is equal to 1, then that means the tangent of theta is equal to 1. So again, we're looking for a solution in our first quadrant where the tangent of that angle is equal to 1, right? Well, again, as far as the symbolic way or the direct way to say what theta is, you take the arctangent of both sides, and this is actually one of our special angles. The arctangent of 1, that's going to be pi over 4. You do not want to write down 45 degrees. Again, all calculus is done with radian measure, right? All right, so we have our differential there, we have our limits there, so the last thing we need to convert over is our integrand, so the square root of 1 plus x squared. Well, if we, I mean, it's a simple thing. We're just going to replace x squared with tangent squared, right? So we will have our 1 plus tangent squared theta. And it's not considered simplified until we've gotten rid of the root, right? It's when we can say we have a perfect square under the square root. That's when we know we've made the significant leap as far as getting closer to the solution. Well, how do we get a perfect square? Go back to our Pythagorean identity. 1 plus tangent squared is secant squared. So this is secant squared theta. And again, because of our assumption that theta is in the first quadrant, all trig ratios are positive in the first quadrant. So then my root and my square will cancel out, and I'm left with secant theta. All right. All right, well, let's put it all together. And again, I always like to write our original integral was from 0 to 1. The square root of 1 plus x squared dx. Well, using this one equation, right? This one equation allowed us to convert everything over to be in terms of theta, right? Using this trigonometric substitution, this definite integral is equivalent to this definite integral. Now it goes from 0 to pi over 4. And then our integrand is secant theta. And then our differential is secant squared d theta. So secant squared theta d theta. So it does simplify a bit. Again, the main goal is that we've gotten rid of the radical, right? And so that goal has been accomplished. But what we're left with now is a trigonometric integral. So we have to switch back to how do we do things like this, right? Well, in the previous section, we looked at a reduction formula for powers of secant, and that's what you would need here, right? That's what you would need here. So the reduction formula for the powers of secant, let me write it over here, just in case you guys don't have it burned into your memory yet. So when you have secant raised to a power that's greater than 2, and you have to integrate that function, well, this is what it comes out to be. It's 1 over n minus 1 times secant to the power n minus 2 times tangent, and then plus n minus 2 over n minus 1 times the integral of secant to the power n minus 2 with respect to theta, right? So this is what we would have to utilize to evaluate this, all right? Now so actually what we can do is let's figure it out with n equals 3 and then see what the antiderivative is and then come back and use our limits, right? So let me do this in our white. So the antiderivative of secant cubed, that is going to be 1 over 2 secant theta tangent theta. Oh, my C and, okay, let me just write the whole thing over. So we have secant theta tangent theta, and then here I have, so then this would be plus 1 over 2 again. So 1 over 2, that's because n is equal to 3. And then we have the integral of secant theta d theta. And this is one of our, again, trig integrals. So this is 1/2 secant theta tangent theta, and then we have plus 1/2, and then this is that ln of the absolute value of secant theta plus tangent theta plus c. Alright, so that is the antiderivative of secant cubed, right? It's a bit of a mess, but we know what it is. So let's use it and evaluate our definite integral. So here's our antiderivative. I'm going to rewrite it. Right, ln of secant theta plus tangent theta, and then all of this evaluated at 0 and at pi over 4. Right? Now, let me just point out, this is where you really start to see the benefit of switching the limits. Because if we didn't switch the limits, and you have the tendency to try to reverse the substitution, you would have to express all of this in terms of x, right? And I mean, it's not that difficult, but it involves using the right triangle and then figuring out all these ratios, the tangent and the secant based on the triangle. But because we've switched our limits, we can evaluate this because now everything is in terms of theta. So at the upper limit, let's see what we have. So we have 1/2. The secant of pi over 4 is the reciprocal of cosine of pi over 4. The cosine of pi over 4 is 1 over root 2. The reciprocal of 1 over root 2 is root 2. So this is root 2. The tangent of pi over 4 is 1. So again, use those same values here. The secant of pi over 4 is root 2, plus the tangent of pi over 4 is 1. So we have the absolute value there. Close that. And then at the lower limit now, the tangent of 0 is 0, right? So we have minus. This term is 0. The secant of 0 is 1. Plus 0, so we have a 1 here. The absolute value of 1 is 1. And then the natural log of 1 is 0. So this term also cancels out quite nicely. So this is what we're left with. Now, because the square root of 2 plus 1 is a positive number, I don't need absolute values. So I'll write this as our final answer. So it's root 2 over 2 plus 1/2 of the ln of the quantity root 2 plus 1, right? So definitely you can see that, you know, these trig substitution problems, they're really two problems in one. First, just converting everything over into theta, and then switching into our trig integral mode and figuring out what procedure or what formula do we need in order to evaluate this thing further. All right? All right, so that was one example. Let's try another one. Now, we haven't done one that involves the sine function. Well, let's try that one. So this would be our second example in this video, but third example overall, including the one that we did in our previous video. So number 3, the antiderivative of the square root of 9 minus x squared, say over x squared, and then dx, right? There is a radical. Now it has a slightly different form. Remember, there are 3 very specific forms. 2 of them involve a difference. So you want to be careful. Is it a constant minus your variable squared, or is it your variable squared minus a constant? Well, when it's a constant minus the variable squared, it ends up being the sine equation that we use, right? So in this case, here's our a, or I should say that's our a squared. So a being assumed to be positive would be 3. And then the equation that we're going to use, x is equal to 3 sine theta, right? And we're going to use this equation again to convert now the differential and the integrand. So first our dx, so the derivative of sine is cosine, so 3 cosine theta d theta. Now let's work on the integrand, and maybe we have room on this side. Let's see if we can get it in here. So we got the square root of 9 minus, when I square this, I end up with 9 sine squared theta, sine squared theta, and then this is all over, again, this squared, it's the same, 9 sine squared theta. Now, again, the goal is to somehow get rid of this root. Well, under the square root, I have a common factor of 9. So this, I can factor out a 9 under the square root. That leaves 1 minus sine squared theta. And there is that Pythagorean identity again. Right, so 1 minus sine squared theta is cosine squared theta. So I have now the square root of 9 cosine squared theta over 9 sine squared theta. And there is our perfect square. So that square root reduces to 3 cosine theta, and then it's over 9 sine squared theta. So that's 1/3. So we have is 1/3 cosine theta over sine squared theta. All right. So that is that's just the integrand, right? We have the differential here that we're going to have to work with, so let's go ahead and do that. So therefore, our original integral in terms of x with this substitution, x equals 3 sine theta, that produces this other integral now in terms of theta. So let me write the 1/3, and then we have cosine theta over sine squared theta, and now I can't forget my dx, right? I have to multiply this by 3 cosine theta d theta. And what happens here? Well, we have a 3 in the denominator. We have a 3 in the numerator. So those cancel out. And then I have a cosine theta times a cosine theta. So I have cosine squared. So what we have left is cosine squared theta over sine squared theta. How do I do this? Well, cosine divided by sine is cotangent, right? So that means this simplifies even further to cotangent theta squared. Well, how does this help? Well, there is a third version of the Pythagorean identity. So let me write all three. If you have sine squared theta plus cosine squared theta, that is 1. If you have 1 plus tangent squared theta, that's equal to secant squared theta. If I have let's see, yeah, so if I have 1 plus cotangent squared theta, that's equal to cosecant squared theta. Therefore, what I can do is I can replace cotangent squared with cosecant squared minus 1. Now, why would I do that? Because this is one of our basic results from Calc 1. We know a function that when we differentiate it, right, will give us cosecant squared. So let's write that down, and then we will be able to actually do our integration. I mean, up to this point, the only calculus that we've done up to this point is this line right here, taking a derivative. Everything else is trigonometry and algebra, right? And even this step is still trigonometry. Right? So cosecant squared theta minus 1 d theta. And the antiderivative of cosecant squared is negative cotangent theta. And then when I integrate 1, I'll get minus theta and then plus c. All right? Okay, we're not done yet. We're not done until we get the integral in terms of x. How do we do that? Using the same equation here, we're going to draw a triangle and we're going to figure out what cotangent theta is based on that triangle. And also that equation we'll be able to solve for theta and figure out what theta is in terms of x. Right? So let's rewrite that equation. So if x is equal to 3 sine theta, then x over 3 is the sine of theta. And there are two big things we can get out of this. So theta is arc sine of x over 3. And then also we can draw a triangle that shows this relationship, right? So if that's my theta, sine we know is opposite over hypotenuse. So the hypotenuse would have a length of 3. The opposite would have a length of x. And then the adjacent would have a length. And it's not a surprise that this radical is the exact same radical that was in our original problem. 9 minus x squared. And you take the square root, right? So looking at this, now again, let's say you wanted to write, before we switched it back in terms of x, remember cotangent theta is 1 over tangent theta, and then we have minus theta there. So if we, based on the triangle, tangent theta is x over the radical. So, well, let's write it down. Tangent theta is opposite over adjacent, and therefore 1 over tangent theta is the reciprocal of this. So it's the radical of 9 minus x squared over x, right? So there we can have, so here's our final answer with everything in terms of x. So the antiderivative of root 9 minus x squared over x squared, this was our original problem, just so that you can see it again. And now we're going to write down its antiderivative after several steps. It is negative root 9 minus x squared over x minus arc sine of x over 3 plus c. All right, so that's our antiderivative. Right. So these trig integrals, they're lengthy for sure, but the thing is they follow a very standard pattern. There's very little variation in these. The things that vary, okay, which equation are you going to use? And even that is pretty laid out. You have 3 possibilities, 3 specific forms, right? Let's do one more example just to get a sense of, again, everything that goes into it. And I want to do one where a couple things are a little bit different, right? Just a little bit different. So this would be our third example today. And let's look at the integral of 1 over, and then the quantity 2 plus x squared to the power 3 halves, right? So let's say we have something like this, right? Well, we don't really see a radical, but it's there. It's kind of in disguise, right? Because this fractional exponent with a denominator of 2 tells me that there's a root in here somehow, right? Now, if you want to see it clearly, this is the root. So it's the square root of 2 plus x squared, and then all of that cubed, right? That's one way to interpret this fractional exponent, right? And then that's with respect to x. So based on the form here, right, it's going to be the tangent equation, but our a isn't going to work out to be a nice integer because based on this, we would say that a squared is equal to 2. We still assume that a is positive, so then a is the square root of 2. And then we're going to use the equation, we're going to let x be the square root of 2 times tangent theta, right? Now once you have this is where, taking the derivative of your substitution equation is standard. So it's root 2 times the secant squared of theta d theta, right? Now let's work on the integrand. Let's see how we can simplify this as much as possible. And we just have to handle this extra 3 with care. So we have 1 plus the square root of 2 plus x squared all to the third power. Well, let's plug in what x is, right? X is the square root of 2 times tangent theta. So this is equal to 1 over the square root of 2 plus, now when I square this, the root goes away and then the tangent also gets squared. So it's 2 tangent squared theta, and then all of this is to the third power. So we have 1 over, now under the square root, we notice now there is a common factor of 2. So factor out the 2, and we have 1 plus tangent squared theta. Again, that's still to the third power. Now, but 1 plus tangent squared, that is secant squared, right? So we end up with 1 over root 2 times secant squared theta all to the third power. Well, I can take the square. Now since it's a product, this reduces to the square root of 2 times secant theta, but then that's all to the third power. So it looks like this. 1 over root 2 secant theta cubed, right? And then, so if we drop these parentheses, it'll be root 2 cubed, which is 2 root 2, right? And then secant cubed. So here is the integrand in probably as simple a form as we can get it. So secant cubed and then theta. All right. So that's our integrand. We have our differential. Now we get to multiply them and see what happens, right? So our original problem, the integral of 1 over 2 plus x squared to the 3 halves power dx with this trig substitution, x equals root 2 tangent theta. what are we going to get? Well, we're going to get an integral now of this 1 over 2 root 2 secant cubed theta times my dx is now this root 2 times secant squared theta d theta. All right. Well, I see a lot of things that are actually going to simplify, right? So it looks like a big old mess at this point, but the root 2 is there, the root 2 is there. We have secant squared in the numerator and secant cubed in the denominator, so I'm going to be left with one factor of secant cubed in the denominator. And this 1/2, right, with this 2 here that's still in the denominator, that can be factored out. So I can put that outside the integral, and all I have left is 1 over secant theta d theta. Now that's a dramatic improvement. And we can improve it even further because 1 over secant is cosine. Right? 1 over secant is cosine. So I'll have 1/2 times the integral of cosine theta d theta. So then I am able to integrate this, and you couldn't ask for a much simpler integral, right? The antiderivative of cosine is sine, so we have 1/2 sine theta plus c, right? And then so we're not quite done because we have to reverse the substitution, right? We have to reverse this. Well, that's where the equation comes in again. So we have our x equals root 2 tangent theta. So that means tangent theta is x over root 2. Tangent is opposite over adjacent. So that tells us exactly how to label our triangle. Does it matter where I put my theta? No, I could put my theta there or my theta there. Once I have my angle, my reference angle made, then that determines how I label things. So if I put my theta here, then this side would be my opposite side, so I label it x. This side will be my adjacent side, so I label it root 2. And then using the Pythagorean theorem, the hypotenuse is going to have a length of this squared plus this squared, so that's 2 plus x squared. And again, it's not a coincidence that it's the same expression that we started with, right? And then based on this, the sine of theta is opposite over hypotenuse. So then here's our final answer in terms of x. So we have 1/2 times x over the square root of 2 plus x squared plus c, right? And that can be written as a nice single fraction, x over 2 root of the quantity 2 plus x squared plus c. All right. So this one just had a couple different things. First, it wasn't just a square root, right? Because we had this extra power of 3 there, so that's one slight modification. Another modification is that our a turned out to be an irrational number, right? Because a squared ended up being 2. That's not a problem. As long as we have a positive constant there, then this procedure will work, whether it's an integer or whether it's something irrational, right? So hopefully these examples have helped. This is not a process that is a 2-second process. You have to sit down carefully, choose your substitution based on what type of radical it is, figure out what the differential is, figure out what the integrand is, and then simplify that as much as possible so that your actual integral, the actual integration that you do, is as simple as possible, right? And yep, so hopefully these have helped, and I'll see you in the next video for more integrals.